All right, let's do an example problem. You can pause the video, go through the question, and then check out the solution. We're trying to find the wavelength of the wave. You and your partner are sitting on the floor. You've got a distance of 3.5 meters between the two of you. You shake it, and it's got one antinode between the two of you. Partner measures the time for 10 vibrations, which is 24 seconds. What is the wavelength of the string? For this, we're going to use the strategy of drawing a sketch of the wave that you made. You should always draw a sketch of the wave that you make. It's just going to help you visualize what's happening a lot easier. Should look like the first wave pattern in the diagram. It is 1/2 of a full cycle of the wave. This is the maximum wavelength for a standing wave on the length of a coiled spring. You can use the equation that shows the relationship between the length of the coiled spring and the wavelength, which is L equals N times lambda over 2. Remember, L is the length of the string, or spring in this case. N is the number of antinodes. Lambda is your wavelength, and then divide that by 2. Rearranging the equation and solving for lambda, we're going to multiply by 2 on each side and then divide by N on each side. Notice the wavelength is twice the length of the coiled spring. Next, what is the period vibration of the wave? Period is the inverse of the frequency. It is the time it takes for one complete cycle. We didn't measure one complete cycle, we measured 10 cycles, 10 vibrations. So the time that it took for 10 vibrations, divide that by the number of vibrations that we had, and that'll give us 2.4 seconds for the the time for one vibration. Now the reason why you'd want to do 10 instead of just 1 is because 1 is really hard to measure. 2.4 seconds is kind of a long time, but as you saw in the activity, in the investigate, that spring moves pretty quick, and it's tough to get your finger on the start and stop of the stopwatch quick enough to get a reliable reading. So the idea is you let it go for 10 times, 10 complete cycles, and see what that total time was, and you average it out, and that'll give you the best possible answer. This is reducing your uncertainty in your measurements. Next, what is the frequency? Well, I just told you that period is the inverse of frequency, so to get, and that period was 2.4 seconds, so to get frequency, we're just going to take the inverse of 2.4 seconds. So 1 over 2.4 seconds is 0.42 hertz, or vibrations per second. Determine the speed of the wave you've generated on the coil. We're going to use the speed equation, which is V equals F lambda. And then substitute in what we have found. We already know that F is 0.42. We know the wavelength is 7 meters. So we get the speed 2.94 meters per second. Or 2.9 if we are accounting for sig figs. The next sample problem. Stretching out a coiled spring on the length of 4 meters. You and your partner generate a pulse that takes 1.2 seconds to go from one end of the coiled spring to the other. What's the speed of the wave on the spring? We are going to use the speed equation. V equals the displacement over time, or the change in the distance. And that gives us 3.3 meters per second. Don't forget about that speed equation too. Sometimes we do. All right, what do you think now? Why does the pitch change when you change the tension in the string? When the string is displaced from its position of rest, the forces between adjacent molecules try to pull the displaced part of the string back toward the original position. This is a restoring force. Increasing the tension in the string increases the forces between the molecules in the string. The increased force leads to an increased acceleration of the mass of the string, which does not change, resulting in a higher velocity and vibration rate. The pitch, therefore, increases when the tension in the string increases.